Okay, so welcome everyone to the ICTS string seminar. Today we are very happy to have Anindya Dey, who will tell us about 3D n=4 mirror symmetry beyond ADE quivers. So please, Anindya, take it away.
Thank you very much for the invitation to speak. So today I'll be, well, firstly, whenever, appropriate, just stop me to ask questions. I mean, it's more fun that way. It would also keep me awake. So please ask questions. So I'll be talking today about 3D n=4 mirror symmetry, which is a very special case of IR dualities in 3 space-time dimensions. Now, this particular talk and the project in general fits into this broader program of studying dualities from a QFT perspective, using a set of techniques used for computing supersymmetric observables in quantum field theories, which go by the name of localization techniques. Now, a lot of work in recent years have gone into checking various dualities that we already know from, let's say, string theory. I mean, QFT dualities that we already know from string theory, and checking them using these new tools. Now, the question that I want to ask in this talk and in the project in particular is to understand whether one can, aside from checking these known dualities, whether one can come up with a systematic prescription for constructing new dualities using these tools. Okay, so that will be the basic sort of crux of the talk. So this is the question that I would like to answer in the limited context of a very specific duality in 3D. All right, so with that in mind, let me present the plan of the talk. So firstly, I'll introduce various basic concepts and make the statements that I just made a little more precise. Then I would basically introduce the technical aspects of the construction, and I'll explain how to use those things to construct new dual theories. And then we'll learn about a particular application of this construction to a set of theories called Argyres-Douglas theories, compactified on a circle to 3D. And then if I have time, I'll discuss how to extend this construction to include dual theories, like dualities, including half-BPS line defects. Okay. All right. So let's begin. Are there any questions at this point? Okay. If not, let's begin. So the main player in this whole business is IR dualities in QFTs. So a set of theories which have entirely different description in the UV, let's say different Lagrangians, may flow to the same theory in the infrared. So this is what we mean by IR duality. And generally speaking, this IR theory might be a strongly coupled theory. So there is an interplay between duality and strongly coupled physics. There are various ways of probing IR dualities in QFT. Now, the specific set of techniques that we are going to talk about in this presentation will be the set of techniques that go by the name of localization, which is, again, as I said, a set of techniques for computing supersymmetric observables, protected observables in a quantum field theory exactly. So let me first begin with a few basic facts about localization that you guys might already know, but nevertheless. So assume a theory T on some d-dimensional manifold MD such that there is a fermionic symmetry Q of the theory that squares to some bosonic symmetry of the theory, L boson. Now, in that case, if you can find a functional V that is invariant under this bosonic symmetry, then you can deform the the path integral, the action of the theory in this fashion. Now, this deformed action has the derivative of the deformed action with respect to t is 0, which means it's invariant as you change t. So in particular, you can fix t to be anything. In particular, you could fix it to be infinity. So when you fix t to infinity, for this path integral to make sense, the saddle points should be at this particular locus, q dot v, q acting on v equal to 0. And if your bosonic symmetry is strong enough, then this will restrict you to a set of points or at times a single point, so that the path integral will essentially reduce to a matrix model. This is completely specified by the gauge group and the matter content of the UV Lagrangian. So this is a generic structure of such a partition function. So there is a classical piece and there is a quantum piece, and both excuse me, both the pieces could be read off from the gauge group and the matter content of the theory. Okay. Now, in general, one can do something which is a little more refined. Namely, one can turn on a set of background fields for non-R global symmetries, and then write the partition function as a function of those global symmetries, or rather as a function of certain background gauge fields for those global symmetries, which we collectively write as A hat. Now, okay, so now given such a gadget, what do? We first note that such objects are RG invariant, and although they're computed using a Lagrangian, but they contain information for the strongly coupled physics. So this is particularly suited to analyze IR duality, where you have a pair of theories X and Y with different Lagrangians flowing to the same SCFT in the IR. You can compute the two partition functions using localization, and then check that they agree as a function of this background gauge field, which is a much more powerful check because you're not comparing two numbers, but you're actually comparing two functions of multiple variables. In general, I mean, the global symmetry that you have would be a non-Abelian symmetry, so there will be multiple gauge fields associated with it. So this is a very powerful check of the duality, and this is usually what is done, morally speaking, in checking various IR dualities. Now, okay, are there any questions at this point? Good. All right. Now, historically, as I mentioned earlier, discovery or understanding QFT dualities have relied very heavily on string theory dualities. There are Weberian constructions like Hanani-Witten construction, geometric engineering of various sorts, and so on. However, we do know that there exist QFT dualities which do not have any known realization in string theory, for example. So this begs the question that can one come up with some systematic field theory prescriptions for generating dualities, starting from some simple ones. So you start from some simple dualities, and then can one come up with a construction that generates the entire landscape of duality? That's the idea. Now, this is the question that I will try to answer in the context of a special class of IR dualities in 3 dimensions. Okay, so to make things more precise, consider a pair of IR dual Lagrangians, X and Y. So X and Y are related by some IR duality. Now imagine I have an operation O that acts on X to give a new Lagrangian, X prime B hat, such that this X prime B hat flows to a new SCFT in the IR. So this O generates a map from one SCFT to another SCFT. Okay. Now, given such a map, I can define a map O tilde on Y such that it produces a new SCFT with a Lagrangian Y prime, with a UV Lagrangian Y prime, such that X prime and Y prime are again IR dual to each other. Okay. So this is the definition of O and O tilde. Okay, so if I can find such a map, then starting from a pair X comma Y, I can generate a new pair X prime Y prime. Okay. Are there any questions on this? Okay.
Yeah,
so that's the plan.
Can I ask you a quick question? So,
yeah.
you are gauging the theory in the UV, right? And then it.
Well, I haven't. Yeah, I will, but I haven't done it. I mean, this is just at a level of a principle, you know.
Yeah. So even at the level of principle, the theory that you're gauging is the UV theory, and then you check if. Then you check the whatever observables in the IR theory. Is that right?
No, so I don't answer the question, but could you repeat the question? Like,
so a few slides ago, I think when you paused for the previous question for the previous last time, you had saying one theory is dual to another, but they were as a functional of background fields. So those were.
That's correct. So that would be X and Y. Yes.
Okay. So these
that would be X and Y. Yes.
Okay. While so these are theories in the UV.
That's correct. They're I mean, yes, they're theories in the UV, Lagrangians in the UV, which flow to the same SCFT in the IR. Yes.
Gotcha. Thanks.
Okay. While X and X prime are not IR dual to each other. Okay. So they are actually they are two different Lagrangians which flow to different SCFTs in the IR. Okay. And similarly, the same for Y and Y prime. So they flow to different SCFTs.
Right.
But X and Y flow to SCFT1, X prime and Y prime flow to an SCFT2.
Gotcha.
Good.
Thank you.
Okay. All right. All right. So now we have to basically look for such a map O. So now we note that we already know of such a map from Witten's paper on SL2Z action. So this SL2Z action that Witten talked about was on a 3D CFT X with some background field A hat with a U1 zero form symmetry. Now this A hat is the corresponding background gauge field for this U1 symmetry. Now such a theory has an S operation, has an SL2Z action, of which the S operation acts by promoting this background gauge field to a dynamical gauge field. And it introduces, as part of the gauging procedure, a term which couples. So if you gauge a U1 if you gauge a U1 background symmetry, the corresponding U1 gauge symmetry has a U1 topological symmetry, and so this term is what realizes that in the action. So that's the S operation, gauging of a U1. And then there is the T operation, which basically corresponds to adding a Chern-Simons term for the background gauge field itself without doing any gauging. Now, a combination of S and T will basically turn on Chern-Simons levels for this background gauge field and gauge it. Okay. So that's the SL2Z action. And generically, this S operation will generate a new CFT as gauging of degrees of freedom are involved in that operation, while the T operation will generally just add some background Chern-Simons levels. Now, what we are going to do is to study a generalized version of this S operation on 3D n equals to 4 quivers. So now we are going to specialize and study some generalization of this S operation on a very special class of theories, which are n equals to 4 theories in 3 dimensions. Okay, are there any questions about this?
Yeah, is there a reason why you don't want to talk about T?
No, I mean, so T should be talked about. In fact, I do talk about it in my paper. It's just that in this talk, I just restricted to n equals to 4 theories. So if you turn on T and then you gauge, typically you break the supersymmetry to n equals to 3 or lower. depending on what matter you choose to have. So that's sort of another story. It's an interesting story, but I'm just going to restrict it to S operations. So all theories I'll talk about will not have any Chern-Simons level.
Okay, so for this Witten SSL2Z, there's also a kind of explanation, or in terms of holographic dual. Is there similar? Is there a similar story here?
For Witten SSL2Z there is, but for the generalization that I'm going to present, as of now I don't know of any.
Okay, thanks.
Okay, all right. So let me. Okay, I'm running way behind time. So anyway, so let me quickly introduce some few basic facts about 3D n equals to 4 physics. So 3D n equals to 4 supermultiplets. They arise as dimensional reduction of 4D n equals to 2 multiplets. So there are 2 distinguished branches: the Coulomb branch, where the gauge group breaks down to the maximal torus, and then there's a Higgs branch, where generically the gauge group is completely broken. And the theory has a dimensionful coupling constant, so it flows in the deep IR to an STFT. Okay, so that's a known fact. Now there's an R symmetry, SU2H times SU2C, which are isometries on the Higgs branch and the Coulomb branch, respectively. Now, in addition, there are some global symmetries associated with the Higgs branch and the Coulomb branch, which are represented as follows. And that is enough to write down, the UV Lagrangian for any 3D n equals to 4 theory. Now, in addition, you have certain 3D n equals to 4 preserving deformations, which we will collectively denote as A hat. And these include the hypermultiplet masses, which are triplets of SU2C and scalar components of a background vector multiplet in the Cartan of GH. And in addition, you have Fi parameters, which are triplets of SU2H and scalar components of a background twisted vector multiplet in the Cartan of GC. Okay, so that is all you need to write down a 3D n equals to 4 Lagrangian with these deformations. All right, so now mirror symmetry is an IR duality which exchanges SU2H and SU2C for a pair of theories. Okay, so that means that it exchanges, in particular, Higgs branch and Coulomb branch, the Higgs branch global symmetry and the Coulomb branch global symmetry, and also the deformation parameters, the masses with the Fi parameters. Okay, so this was like a breezy summary of mirror symmetry. Now I need to introduce quiver notation for the Lagrangian theory that I'll use for the rest of the talk. So this is like a brief summary. So this circle node will represent a UN vector multiplet. The ones with double circle will represent an SUN vector multiplet. Circle with a box, it's a certain number of hypers in the fundamental. Line connecting 2 circles would be a single bifundamental. And then if there are multiple bifundamentals between 2 gauge nodes, then I'll explicitly denote that with an integer p. So in this case, for example, there are p g times g prime bifundamental hypers. Okay, is this notation clear? Okay, all the circles are vector multiplets and all the squares are hypermultiplets. Good. All right. Now, additionally, I'll talk about another kind of matter, which is like Abelian matter, which I'll denote with this blue line. So this blue line indicates a single hypermultiplet that's charged under the U1 subgroup of this, and this vector multiplet. Okay? And the corresponding charges are given as Q1, Q2, and Q alpha. Now, in some special case, you can also have a single, you can have a hypermultiplet that's charged under a single U1, and like this. And this is how I'll denote it. So this notation means that there are p hypermultiplets charged under the U1 subgroup of this UN alpha plus 1. And the charge is Q alpha plus 1. Okay. Is the notation clear? Okay. So that's all I need from the perspective of quiver diagram. Okay, so now we are ready to introduce this generalization of S operations that I was talking about. So firstly, I'll consider quivers in a certain class that I call class U. So these are good theories which have these are good theories such that the Higgs branch global symmetry of this theory has a subgroup which is a product of unitary factors. Okay, so remember in Witten's case, he demanded that the 3D CFT had a U1 global symmetry. So the generalization of that, somewhat obvious generalization of that, is you have a subgroup in the Higgs branch global symmetry, which is a product of these unitary factors. Okay, now given such a theory, X in class U, so this is how I denote it generically. Everything else is hidden. I have just shown up a UM alpha global symmetry. I can define 3 different operations. The first operation is the plane gauging operation. So I take this UM alpha node. I divide the node into a UM alpha minus R alpha and a UR alpha node. And then I gauge the UR alpha node. Okay. So this is just a direct generalization of the gauging operation of the S operation of Witten. Now, in addition, I can think of the flavoring operation. Sorry. So in addition, what I can do is that I can take this UM alpha node, break it into 2, R alpha and M minus R, and then flavor this with some additional hypermultiplets. Okay, so this is so I'm not gauging in this operation. So this is just a flavoring operation. Okay. Now another operation that I can perform on the quiver is the so-called identification operation, where suppose there is a UM alpha minus 1 and the M alpha node. I take out R alpha node from each and I identify that. Okay. So there were like a set of background gauge fields. So I'm just identifying part of them. You can also think of them as, breaking a UR alpha times a UR alpha to the diagonal of the 2. Okay. So these are these 3 operations that I can perform on a given quiver of class U. So now I can define what is the generalization of the S operation of Witten. So this I call as an elementary S-type operation. And this operation involves all possible combinations of identification and flavoring, followed by a gauging operation. Okay. So you first identify whatever flavors you want to identify, and then flavor the new identified node. And then finally, at the end, you gauge it. So N1 and N2 could be 0 or 1. So which means that all the possible things you can think of. I'll classify them in a second. But so this is what defines an elementary S-type operation. And just like Witten's S operation, this takes you from an SCFT, from one SCFT, which has a UV Lagrangian X, to a new SCFT with a different Lagrangian X prime. Okay. Now, from the definition itself, you can see that there are 4 types of elementary operations that you can think of. The first one is the plane gauging operation, where N1 and N2 are both 0. Then you have the flavoring gauging operation, where N1 is 0 and N2 is 1. And then you can have the identification gauging operation, where you set N2 to 0, but N1 is 1. And then finally, you have the identification flavoring gauging operation, where both N1 and N2 are 1. Okay. So let me pause here for questions if there are any. So is the definition clear?
Yeah, I'm sorry, I have a very naive question. So
yeah, sure.
Maybe it's already implicit in this quiver business, but once you do these operations, the theory that you obtain is still SCFT?
Yeah, so we are now in completely the 3D regime, right?
Mm-hmm.
So the theory that as long as a theory is a good theory, doesn't have as long as the UV, as long as you know enough about the IR physics from the UV Lagrangian, which is the definition of good theory, then you know that you have some SCFT in the IR just because it's 3D theory. So it's a dimensional coupling constant, right?
All right. Okay.
So it will always flow to some SCFT in the IR.
Mm-hmm.
So yes, that's the advantage of having. So although we are dealing with Lagrangians, the Lagrangians are always related to some SCFT.
Okay, thank you.
Good, okay. Okay, other questions? All right, so given this definition, one can then define a generic S-type operation, which is a combination of any number of these elementary operations. So you basically define one elementary S-type operation, and then you sort of consider a sequence of them at different nodes. So alpha denotes the particular flavor node at which you're performing the operation, and so on and so forth. And so this is how it how you define a general operation. Now I should probably should have commented that there's this object P that's sitting up there, and I didn't explain what it is. So this P is a permutation matrix that appears in the definition of each of these gauging, flavoring, and identification operations. So if I just go back for a second to the gauging operation, let's say. So you saw that I took a UM alpha quiver and broke it down to a UM alpha minus R alpha times UR alpha quiver node, right? Now here I made a choice of which of the background gauge fields corresponding to UM alpha should be considered as a UR alpha background gauge field, right? So there was a map of background gauge fields from UM alpha to the other side. And this choice is encoded in this permutation matrix P. Okay, so for each P, you make a different choice of how to organize the background gauge fields into this new background gauge field. All right. Okay, so these are the two definitions. So now let us review the structure one more time. So consider a pair of Lagrangian series XY where X is in class U. So then I have a map, this O alpha P, that takes me from X to X prime in a manner that I just described. And so the idea is now to figure out what is this dual map O tilde that takes me from Y to Y prime. Okay. Now to find this map, I need to figure out, I need to actually resort to localization computation. So this computation is easiest for the S3 partition function and the S2 times S1 superconformal index, but you can as well do the same computation with other observables. So let me quickly mention how this is done. Okay, so let me pause here for questions if there are any.
Again, I have a naive question. So is it obvious from your construction that S square is 1 minus 1 or 1, whatever?
So here it won't be. So yeah, in SL2Z it would be. And so if you just restrict this construction to a single U1 gauging, just like Witten, then you will get that same answer, like S squared will be equal to minus 1. So you'll see it here in, so if you do an S square, you'll get the same theory with the sign of the masses reversed. So M will become minus M, basically. But generically speaking, there is no such relation because there is no such group structure. unless you're doing like a U1 or a U1 to the n, in which there's an sp2nz structure.
I see. Okay, thanks.
Okay, so generally there is no group structure that is understood yet, because I mean mostly because of the flavoring thing that I'm doing. Yeah. So it's like adding extra hypermultiplets in the system.
Okay, thank you.
Good. Okay. All right. So now let's try to understand this. Sorry. Yeah. So I'm doing a schematic picture so that that basically applies to both the partition function and the index or any other observable for that matter. So so the theory X, as we learned earlier, has a partition function that is given by a matrix integral of this form, where the X integrand could be simply written down from the gauge group and the matter content of X. And similarly, there's a matrix integral for Y, where the integrand could be written down from the gauge group and the matter content of Y. Okay. Now, IR duality implies that Z of X and Z of Y are related in this fashion, where ZXY are certain contact terms that depend on these background gauge fields. Okay. Now, the S-type operation that I just defined could be implemented at the level of the partition function by simply introducing an operator in this matrix integral, which is given by Z O alpha P, and it's a function of the background gauge field A hat, which is being integrated, and some new background gauge fields which are introduced. So these collectively could be the different topological, this could be background fields for the topological symmetries that are introduced, or the symmetries associated with the hypermultiplets that we have introduced. So both are contained in this B hat. Okay. So this is the partition function for the theory X prime B hat. Okay. And this ZOP could be constructed from by knowing how this OP is constituted of the gauging, flavoring, and identification operation. So once you know that, you know exactly what operator should go in there. Okay, so it's a very well-defined operation. All right. So now, given ZOP, I can define a dual function, which I call ZO tilde T, and that is given by an integral over ZOP with this extra function F sigma A hat, which is the A hat dependent part of this integrand. Okay. So in the simplest case, this dual function is simply a Fourier transform. Okay. Now, in more complicated situations, it's different, but the basic case would be that of a Fourier transform. So once you construct this dual function, then there's a very simple way of writing down the dual partition function, which is by introducing this dual function inside the matrix integral. Now, note that, okay, so this is an expression for the dual partition function. So this will be our working definition sort of for the dual action or dual map O tilde that we defined. Now, note that it's not clear from this expression that that the dual theory Y prime is Lagrangian. Like, in general, we know of examples where the mirror of a Lagrangian theory may not be a Lagrangian theory. However, if Y prime turns out to be a Lagrangian theory, then its gauge group and matter content and so on, that could be read off from this expression. Okay. So otherwise, you can probably look at the global symmetries of the mirror theory and so on and so forth. But if it's a Lagrangian theory, if Y prime turns out to be a Lagrangian theory, then you can simply read out everything from this dual partition function. Okay, so that's how the map on one side of the map O and the map O tilde, they are implemented at the level of the partition function. Okay, so let me pause here to take questions if there are any.
So how would one know that whether it's a Lagrangian theory or not?
just from by looking at this expression itself, you'll know. So this could be organized in terms of vector multiplet and contributions, hypermultiplet contributions, and so on and so forth. So you can rewrite the right-hand side as in the standard form. So as you know, I mean, for example, the S3 partition function could be written as as some classical piece times some one loop piece, where the one loop piece includes a vector multiplet contribution, hypermultiplet contribution, and so on, right?
Okay. Yeah.
So here, all I'm saying is that if you compute it in this fashion, then the answer that you get will again be, I mean, you can again recast that answer in terms of by very minor, change of variables maybe into a vector multiplet contribution and a hypermultiplet contribution, and then read off the content from that. Does that answer your question?
Oh, yes, it does. Thank you.
Okay, other questions? Okay, so now I'm going to focus on a very special case of these S-type operations, which is the case of Abelian operations. Now, note that these Abelian operations are not the S operation of Witten, because although it involves gauging a U1, it could also potentially involve the flavoring and the identification operations, which were not part of Witten's construction. Okay. So Abelian operations mean that you can do whatever identification and flavoring you want to do, but at the end you gauge only a U1 global symmetry. Okay. So in other words, this R alpha that I was writing down, R alpha is just 1. Okay. So now there is a very interesting result for Abelian operations, Abelian S-type operations, and it is as follows. If a quiver gauge theory X prime is related to another quiver gauge theory X by a sequence of Abelian S-type operations, and X has a Lagrangian mirror Y, then X prime is guaranteed to have a Lagrangian mirror. Okay. So what am I saying? I'm saying, let's suppose that you give me a extremely terrible looking quiver gauge theory X prime, and I can somehow show you that it follows from a theory X, a simpler theory X, by a sequence of Abelian S-type operations. Now, in addition, if this X is this theory X also has a Lagrangian mirror Y, then X prime must have a Lagrangian mirror. Okay. Is the statement clear? Okay. Now, for Abelian operations, there are very clear recipes for the 4 type of dual elementary operations that I mentioned earlier. So the dual operations for these 4 elementary operations can be very simply understood at the level of the quiver. Okay. So firstly, the gauging and the identification gauging operation. So this simply amounts to ungauging a U1 subgroup of the gauge group Y. Okay. So this is very much similar to what Witten's S-type operation would do. But then there is the flavoring gauging and identification flavoring gauging operations, for which okay, so firstly, if it's ungauging of a U1 subgroup of the gauge group of Y, then the resultant gauge theory Y prime is obviously a Lagrangian case, right? Now for flavoring gauging and identification flavoring gauging, the generic quiver is slightly more complicated. So it consists of 2 subquivers. One is this Y, which was there. And then the second subquiver is a chain of U1 with n alpha minus 1 nodes. But these 2 subquivers are now connected by an Abelian hypermultiplet, which means that this is a hypermultiplet that's charge 1 under this U1 and has charge QP under various U1 subgroups of the gauge group of, so suppose Y has several unitary factors, then this particular hypermultiplet is charged under the U1s of those unitary factors, okay? And the charges, corresponding charges are given as QP. So this is the general form of the quiver that arises from a flavor engaging and identification flavor engaging operation. So as you can see, in each of these cases, the dual theory Y prime that you obtain at the end of the operation is a Lagrangian theory. Okay. While X prime is obviously Lagrangian because of the construction that we did. Okay, good. An additional thing that you learn from this is that if you start with a unitary, if you start with a pair of unitary theories, which means that your quiver gauge theory has unitary gauge groups, then a unitary theory will always lead to a unitary theory, unless you have some gauging or identification gauging operation. So note that in the flavor engaging or the identification flavor engaging, there is no overall gauging of U1. So if you had a UN, it would not become, for example, an SUN. Okay. So the max that can happen is that you have these two subquivers and some additional hypermultiplets, but you don't produce special unitary gauge groups from unitary gauge groups. Okay. Good. Is the statement clear? Okay. Okay, so this is something that we are going to use in our application in the next section. So let me pause here and take questions if there are any. So this is basically the structure, the construction that we are going to use now to generate to construct new 3D duals starting from certain given ones. Good. Okay, so then what is the strategy? The strategy is to start from some very simple, quiver pairs like linear quivers with unitary gauge groups, and perform a sequence of these S-type operations on them and generate new 3D duals. Okay, so that's what we are going to do in the next section. So the particular system that we are going to use are the 3D Lagrangians for Argyres-Douglas theories compactified on a circle. So before I actually talk about the 3D Lagrangians, let me give you certain basic details about Argyres-Douglas theories. So these are 4D n equals to 2. So Argyres-Douglas theory is a generic name for 4D n equals to 2 interacting SDFT with Coulomb branch operators having fractional scaling dimensions. Now, first examples of this kind was realized at special points in the Coulomb branch of Lagrangian theories, where electric particles and magnetic BPS particles simultaneously became light. Now, so subsequently, there were various constructions of these Argyres-Douglas type of theories. So in particular, they were obtained by compactifying type 2B superstring theory on certain singular Calabi-Yau hypersurfaces. And then there was a huge dictionary of class S construction, where 6D2, 0 theory was compactified on a sphere with an irregular puncture and possibly an additional regular puncture. So each of these constructions basically led to a certain classification of some subclass of Argyres-Douglas theories, and there was much overlap between the two. Now, what we want to consider is such an SDFT compactified on a circle and then flown to the IR. This leads to a 3D SCFT, which is generically non-Lagrangian, but may have a Lagrangian 3D mirror. Okay, so the idea is that you take the 4D theory, compactify on a circle, flow to the IR, you get a 3D SCFT. Now the 3D SCFT itself may not have a Lagrangian description, but it might have a 3D mirror. Okay, now a lot of work went into finding this 3D mirror for theories that could be realized in class S. And the upshot of this analysis is that the mirror Lagrangian, the 3D mirror, can be read off from the class S data. And there is a large literature on how to basically do that. I'm not going to discuss the analysis in detail, but I'm going to use the final result as sort of my starting point in the next slide. Okay. So now our strategy would be to show that the class S mirror that was constructed itself has a Lagrangian mirror, which would imply that the 3D SCFT obtained by compactifying on the Argyres-Douglas theory in a circle itself has a Lagrangian description. Okay, so if you can show that the mirror is of the 3D mirror is Lagrangian, then that it's a Z2 thing. So you show that the dimensional reduction of the Argyres-Douglas theory itself is Lagrangian. Okay, so that's the strategy. And this can be explicitly worked out for various families. So the GG prime families, for example, for arbitrary S and P, and the DPSUN family, which is another family which I'll introduce. Okay. So is the program clear? Is it? Should I explain? Okay. Any questions at this point? Running way behind time. Yeah, sure.
Just a quick thing. So what you mentioned earlier, the theorem sort of that once you have the U1 thing, then the S mirror, if one is Lagrangian, then the other one is too. So that's going to prove somewhere, or that's something you have proved here, or?
That's something that I've proved in my paper from last year. Yes.
Okay.
So I mean, you can sort of see that explicitly from what I just mentioned. So if you look at so these are the 4 operations. There are only 4 elementary operations. And I've stated here the duals of the 4 elementary operations, all of which are Lagrangian. So now if you put a sequence of them, then all you can produce is only Lagrangian stuff.
Okay, thank you.
Okay, so that's the logic. So it's a very simple theorem. All right. So now let's discuss the first family, the GG prime SCFTs of Chakotay, Naivsky, and Vafa. So these are obtained by compactifying type 2B on a 3-fold singularity in P4. And the 3-fold is labeled by a pair of simply laced thinking diagrams, G and G prime. And in our case, G and G prime are both of A type. Okay. Now in the class S, this is realized by a single irregular puncture. Now, the 3D mirror from class S is a complete graph. So this is a result that I'm stating. This is not something that I'm trying to prove. So the 3D mirror is a complete graph of S plus 1 vertices and edge multiplicity P. So let's look at an example. So let's say S equals to 2 and P is completely generic. Then the class S mirror is this guy. So each vertex, so there are 3 vertices, and each vertex corresponds to a U1 gauge node, and each edge with a multiplicity P denotes P hypermultiplets, which transform as bifundamental under this U1 times U1. Okay. All right. Now you see that there is no fundamental flavor here in this. So, there will be an overall U1 that decouples from the system, and you get a quiver, which looks like this. Okay, so this is the class S mirror that's given to us. Now, the question is, does this guy have a Lagrangian mirror? Okay, so that's the question that we're going to ask. If this guy has a Lagrangian mirror, and we know that Lagrangian, then that is the Lagrangian of the theory that you obtain, or rather, that's the Lagrangian of the SCST that you obtain by dimensionally reducing an Argyres-Douglas theory on a circle. Okay. All right. So the way to proceed is to start from a linear quiver, which is a very simple object, and take this. So consider a U1 theory with 2p flavors, and you separate the 2p into a UP and a UP, and you break the UP node into PU1 nodes. Okay? And then you identify it to a single U1 node, flavor it with additional P nodes, and what you get is this. So it's an identification, flavoring, and gauging operation. Okay, is this operation clear? All right. So now one can look at the dual operation. So on one side, you have U1 with 2p flavors, and you do this. Now the mirror dual of this U1 with 2p is this quiver. And the dual operation, what it does, if you remember, what should happen in a identification gauging identification flavoring gauging operation, is that a new tail should be added to the quiver, which is what's happening. So this is a new thing that's added. So that's the dual of this operation, and hence this is, as you can see, manifestly a Lagrangian theory, and this corresponds to the Lagrangian that you get for the 3D. I mean, this is the Lagrangian for the 3D SDFT for S equals to 2 and generic P. Okay, so this is a direct way of proving that, at least in this case, that the SCFT that you get by dimensional reduction is indeed a Lagrangian theory. Okay. Okay. Questions? All right. Okay. The second thing that one can do is the DP-SUN family. Okay. So this also admits a type 2B realization on a threefold singularity. On a threefold singularity in C3 times C star, and it's labeled by this positive integer P and an ADE singularity G. And in this particular case, we take G equals to SUN. And the class S realization of these guys involves an irregular puncture and a full regular puncture, a maximal regular puncture. All right. And again, the 3D mirrors are known from class S. So let me unpack the notation a little for you. So this means that you have, so the mirror theory corresponds to a linear quiver, where A is a tail, which is P minus 1, 2P minus 1, and so on. So this is a unitary tail. And B is also a unitary tail, a minus 1 all the way to 1. And then this is connected to a complete graph by fundamentals of different multiplicities. So every edge here is worth M1. Every edge here is worth M2. And the edges of the complete graph itself are worth Mg. So all these are parameters which are determined once you specify P and N. Okay. The details are not so important, but just generally this is what's going on. Now, how do you construct this using S-type operations? Well, you start with a linear quiver, which is very simple object. You break up the flavor symmetry in this fashion. You identify and flavor gauge it, and then you continue doing it. And if you do it M-1 times, so here I have drawn the figure for M equals to 3. So you see, after 2 operations, I get back what I need. So if there were m vertices, then I would have to do m-1 S-type operations to get the quiver that I need. Now, the thing to note here is that the S-type operations that I'm using, they are A, Abelian operations, and B, they are all identification flavor engaging operations. Okay. So remember that the corollary that we proved was that if your S-type operation is only made out of flavor engaging or identification flavor engaging operations, then a unitary theory will always lead to another unitary theory, right? So this leads us to certain general features of the mirror theory. Number one, and most importantly, the 3D mirror Y prime of the quiver gauge theory X prime must be a Lagrangian theory. Okay, so this in particular implies that when you dimensionally reduce a DP-SUN, you will always get a 3D SCFT which has a Lagrangian description. And this exercise that I just did actually allows you to construct that Lagrangian explicitly. Okay, I think this is a major result. Secondly, it tells you that the gauge group of Y prime, that is the Lagrangian theory that you just constructed, must be a product of unitary factors. So there will be no special unitary factors, for example. Okay. And additionally, aside from fundamental and bifundamental matter, the quiver will involve several hypermultiplets, which are only charged under certain U1 subgroups of the unitary factors. In other words, those blue lines that I was drawing. So aside from fundamental and bifundamental hypers, those blue hypermultiplets would also be there. Okay. Okay. So now you can do the same thing for p greater than n, and the same logic basically flows. And again, you show that the corresponding 3D SCFTs will have Lagrangian, and the Lagrangians will have unitary gauge groups. And the only additional piece that's interesting will be these extra Abelian matters that come in. So just to give you a simple example, so if you think of p equals to 4 and n equals to 6, this is the class S mirror that you get. So here I decouple the overall U1, and this leads to the quiver on the right hand side. And the corresponding construction that I just mentioned in this case gives you the Lagrangian Y prime. Okay, so you see it's a linear quiver with unitary gauge groups decorated by this extra hypermultiplet, which has charge 4 under this U4 and charge 1 under this U1. Okay, so this is an example a simple example where you explicitly know the Lagrangian. Okay. Okay, let me pause here and take questions. Maybe I was going too fast. Okay. All right. So then, okay. So then, what we have shown is basically for these whole families of DP-SUNs and AA prime Argyres-Douglas theories, whenever you compactify the Argyres-Douglas theory, which is a non-Lagrangian theory, on a circle, the 3D SCFT that you get is always Lagrangian. Okay. So this is an upshot of this exercise. Now, very recently, there is another paper by Cyril Closet and friends who also study the compactification of a DP-SUN SCFTs from a slightly different perspective. So what they show, what they observe is that these DP-SUN SCFTs can be written in a particular fashion, can be written in a partially weakly coupled description, which means that it could be written as a set of isolated SCFTs in 4D, which are glued together by SUN vector multiplets. Okay, so all these DQ curly DQ n minus n and so on. So these are isolated SCFTs with SUN minus n flavor symmetry. And they could be glued together by these SUN vector multiplets. Now, when you take such a system and you flow to the IR in 3D, you compactify on a circle, the SU factors survive to 3D because they are conformal factors. And then these isolated CFTs become something, let's say some theory T. So then the end result is something of this form, where you have some theory T1, T2, and T2 all the way to Tm minus 1 glued together by SU factors. Okay. So now this was their prescription for the 3D theory that you would get on dimensional reducing on a circle. Now, these theories, T1, T2, and so on, turn out to be chains, like linear chains of unitary gauge groups with bifundamental matter. Okay, so then the 3D theory that the 3D Lagrangian that they propose is very clear. It's a set of chains of UNs interspersed with these SU factors. Okay, is the construction clear? Okay, so evidently, I just told you a Lagrangian for the same theory, and here is another Lagrangian. So obviously they are not the same because I emphasized that there are no special unitary factors in the Lagrangian, while they do have explicit SU factors. So what's going on? So comparison between these two results suggests that we have an IR duality between two theories, or these two sets of theories for every dp-SUN. Okay, so on one side, you have a linear chain of unitary and special unitary gauge groups with fundamentals and bifundamentals. On the other side, you have a generically nonlinear quiver involving only unitary gauge groups and decorated with this Abelian matter, in addition to fundamental and bifundamental hypers. So an IR duality, which is of this form, but not related to any of the Argyres-Douglas theories, is this. You have an SUN with 2n minus 1 flavors on the one side, and you have a UN minus 1 theory with 2n minus 1 flavors on the other side. Additionally, the unitary theory has a single hypermultiplet, which is charged under the U1 subgroup of UN minus 1, and the charge is n minus 1. Okay? So the claim is that these two are dual to each other. And the n equals to 2 version of this should be clear, should be familiar to people. So that is an SU2 theory with 3 flavors, being dual to U1 with 4 flavors. Okay, so this is just a statement that the A3 quiver gauge theory is the same as a D3 quiver gauge theory. Okay. And for the n equals to 2 case, you can even do you can even write down a type 2b description, and everything is fine. So this is just a generalization of that for arbitrary n. So this you can, for example, check using the S3 partition function, and they agree. The two sides agree if the FI parameter on the RHS is set to 0, as we have here. Now, an IR duality associated with a dp-SUN is of this form. So on the left-hand side, we have a quiver, which is of the type proposed by Close and friends, and the right-hand side is the Lagrangian that we just discussed. So the claim is that these are IR dual to each other, provided the FI parameters are adjusted in a certain way, which is indicated in the diagram. Okay, now this can be explicitly checked again using S3 partition function, that the partition functions agree, provided you you tweak the, provided you relate the FI parameters of these two nodes in this specific way. Now, the advantage of having these unitary gauge groups from this S-type operations is that the Coulomb branch symmetry is manifest in that class of theories, while it's not manifest in the theories that Close and friends talk about. So remember that both these theories are mirror dual to this particular quiver. Now, this quiver has a Coulomb branch symmetry of U6, and that should be a manifest Higgs branch symmetry in both these objects, which is true. You can see that there are 6 hypermultiplets here, 6 hypermultiplets here. So there's a U6 coming from that. But in addition, this guy also has a U1 cube Higgs branch symmetry, which means that these guys should have a U1 cube Coulomb branch symmetry. Okay. Now the Coulomb branch symmetry is obvious from here. So there's a U1 for each node, which gives this U1 cube Coulomb branch symmetry. But for this quiver, you only have a U1 square that's manifest in the UV Lagrangian. So the third U1 sort of appears in the IR as an accidental symmetry. So that's the advantages of the quivers that we have derived, because since they're completely made out of unitary gauge groups, all the global symmetries are manifest. All right. Okay, so I'll just pause here and, if there are any questions before I just launch into the last section. Any questions on what I said? All right, so then let me just take, can I take 5 more minutes?
Yeah, sure, 5 minutes time.
Yeah, so I just 5 more minutes to close off. So now, what I just said about bare theories could also be said, could be said equally well for theories with line defects. So in particular, if you have half-BPS line defects, there are 2 kinds in 3D n equals to 4, the Wilson defect, which preserves a certain 0,4 SUSY within the n equals to 4 algebra. And there is the vortex defect, which preserves a 2,2 SUSY. And this is engineered by coupling a 2,2 superquantum mechanics. So I'll skip the details because I've been over time, but the essential point is that pretty much everything that we did could be equally well, could be generalized to theories containing Wilson defects and vortex defects. So a particularly important problem that people care about is the map of Wilson defects to vortex defects under mirror symmetry. Now this was not known for a very long time. So say Hanani-Witten came in mid-90s, and the first paper that essentially addressed this map of vortex defects to Wilson defects under mirror symmetry for non-Abelian theories came in 2015. So nearly like 20 years after Hanani-Witten. So it's an extremely difficult problem, and this 2015 paper by Assel and Gomez, they studied these mirror maps for linear quivers consisting of unitary gauge groups. So a very simple system, which has a Hanani-Witten realization. Now, from a type 2B construction, they found the precise form of the 3D 1D system, the vortex defect, that is dual to the Wilson defect in the linear quiver. So this is the form of the 2,2 SQM. I'm not going to go into the details, but there's a clear way of reading off the vortex defect from this superquantum mechanics. Okay. So given that, what we can do is we can start with a quiver gauge theory, X, which now is decorated by either a Wilson defect or a vortex defect. And we consider a map O alpha, which takes us to a new theory X prime, but now it's decorated by a defect of the same type, which we call D prime. Okay. And now we define the S-type operations using flavoring, gauging, and identification operations. Now you can also add to it a defect operation, which basically turns on Wilson or the vortex defect for the newly gauged node. Okay. So then the whole prescription that we had just follows through. You again start with X and Y, which are mirror dual to each other, and then define these maps O and O tilde such that x prime and y prime are again mirror dual to each other, and the line defect d prime and d prime check are also dual to each other. Okay. So that's just something a complete parallel to what we saw earlier for the partition function computation. All right, and so here is an example of how to realize a vortex defect in a D4 quiver. So you start with a linear quiver, a vortex defect in a linear quiver, which is a coupled 3D 1D system. It is dual to a Wilson defect in the corresponding mirror dual. So what you do is you take this linear quiver, you break this U2 into a U1 times U1, flavored this U1 with a additional hypermultiplet. And then in addition, you break this U2 into a U1 times U1 and gauge this U1. So there are 3 gauge groups that there are 3 nodes that you're gauging. So this object is an honest vortex defect in a D4 quiver. Okay, so we started with a defect in a linear quiver. We have ended up with a vortex defect in a D4 quiver. Okay, so this is how you engineer defects in quivers that are not linear. And then on the dual side, you basically you start from a Wilson defect in this theory, and you reduce to a Wilson defect in a mirror dual theory. Okay. So at the end of the day, you started from this dual theory and ended up with a defect in a D4 quiver and a Wilson defect in the mirror dual. Okay, so this is a very simple example, but this you can carry on with more exotic examples. So the paper that I wrote in March is basically completely about how to generate defects in D-type theories, starting from defects in linear quivers. Okay. All right. So I'll skip that and let's just talk about the future direction. So obviously, extending this construction presented here to 3D n equals to 2 dualities would be very interesting. And that's where these key operations will become useful. So we can turn on, in those cases, generic Chern-Simons level for non-Abelian gauge groups and dualities involving those kind of theories. There is the question of bosonization dualities that you can probably derive from these new dualities. So starting from these 3D n equals to 4 dualities, you break the supersymmetry stepwise to first to n equals to 2, and then equals to n equals to 0. And possibly there is a larger zoo of bosonization dualities that could be studied in this fashion. In the paper from March, I only discussed line defects, mirror maps of line defects for D-type quiver gauge theories. Now, of course, one should think about theories beyond the ADE type, and the mirror maps of those are not known, and that's a work in progress. And then finally, this curious IR duality that we uncovered while studying the circle compactification of Argyres-Douglas theory, which involve like unitary theories with Abelian matter on one hand, and unitary and special unitary theories on the other hand, would be an interesting thing, and that's also a work in progress. So I would like to end there. Thanks for your attention.
Okay, thank you very much, Anindya, for the great talk. Is there any question for Anindya? Yes, so I was wondering something. When you say that the new dualities that you propose, is it just that the partition function are the same, or is it more general than this? What you can show? I mean.
Right. So we checked the global symmetries agree. That was the first check. So in the simple cases, we also checked that the moduli spaces agree on both sides. And then we also showed that the partition functions agree on both sides. Now, so these are all strong checks, but one still needs to understand more stuff. Like for example, how do line operators go from one side to the other? So there are n number of checks that you should possibly be doing. But for now, we have checked the moduli space and the partition function.
I see. Okay.
Yeah.
And what about the superconformal index?
Well, so in the simple cases, we check the Hilbert series on both sides, which is basically some limit of the superconformal index. But yeah, we expect those to agree.
Okay.
Yeah. So so the interesting thing is that you have to turn off for the partition function to agree, S3 partition function to agree. You have to turn off the FI parameter of the. Sorry, just to go back to the. So you have to turn off the FI parameter of the UN-1 theory, the unitary theory, to have an agreement. So it's not, it's not a duality in the fullest sense of the term. So when we think of dualities, we think of turning off every deformation and all of that agrees on the two sides. So here it's a little more restricted, it seems. So you always have to turn off this FI parameter in the UV. And the reason is that there's a U1 symmetry, but that's of the SUN theory that only appears in the IR. Okay, so this is sort of the new tweak in the duality, which we have to understand better. So it's not a duality with all deformations turned on.
I see. Okay. Thanks.
Sure. Okay, other questions, comments?
And what happens if you reduce these dualities to 2 dimensions? Is this trivial or?
Well, from 3D to 2D it's tricky. I mean, there are lots of, we haven't tried doing it, but there are a lot of technical details that go in when you reduce things from 3D to 2D.
Okay.
So yeah, so from 4D to 3D is relatively easier, but 3D to 2D there's a lot of things that you need to take care of, but we haven't tried that.
I see. Okay.
Yeah. So for us, it's like an observation that this set of Lagrangians that Cyril and friends found, and the Lagrangians that we found from this S-type operation construction actually are related in this way.
Okay.
Yeah. So the n equals to 2 thing, it's probably well known to many people, like an SE2 with 3 flavors. You can realize it as a type 2B, like Hanani-Witten kind of a setup, where you have an orientifold 5 plane, and D3 branes ending on orientifold 5 plane. And if you S-dualize that, what you get is a D3 theory basically, but that's just an A3, which is mirror to U1 with 4 flavors. So here in this case, n equals to 2, and so you see it's a U1 theory, and there are 3 flavors from here, and this extra one then has a charge 1 because n equals to 2. So it just becomes U1 with 4 flavors.
I see. Okay. And since you mentioned the class S theories, I was wondering, is there like an evaluation with like something like the 3D correspondence?
Say it again. I didn't understand.
I was wondering whether there is any relation with the 3D correspondence, like the type of theories that you get from the 6D02.
You mean the Lagrangians that I have? Are they?
The theory that you study, because you study reduction of classes theories?
That's correct, yes.
So there are also like reduction of the 6D 0,2 theories.
Yeah, but
so
those
that's why
theories are usually slightly different. I mean, those are the so-called class R theories, right? Which are
yeah, okay. So
they're
not the same because they have this twist, maybe, or is it?
Yeah, so those are, generically speaking, 6D theories compactified on 3 manifolds.
Yes, but isn't it the same here? Because you compactify on the Riemann surface and then on S1?
Yeah, but that's a very special case. Yeah, it's a special case.
Okay.
Yeah.
I see. Yes.
But generically, you would have a right.
Okay.
Yeah, I'm not sure. If there is anything insightful that I can say about the 3D correspondence picture, but yeah, I didn't use much of the. I mean, the only class S information that I basically used were the structures of this mirror theory.
I see. Okay.
So aside from that, the entire computation was a 3D computation.
Okay, thank you. Any other question for Anindya? Okay. If not, let's thank Anindya again for the great talk.
Thank you.
Thank you. So let me end the meeting now.
Okay.
Bye. Bye all.